Welcome, everyone. Good afternoon. Thanks for joining us for our monthly Rockin' pop-up with the Santa Cruz Museum of Natural History. I think we've done this a couple of times over the past several months where we've opened the Rockin' pop-up with sort of a message of, we hope you're doing okay. And maybe this can be a nice reprieve from what might be a stressful afternoon for many people out there today. So we are going to be having a little bit of fun talking rocks, maybe appropriately talking about some kind of apocalyptic events that have occurred in the Earth's history. So on that note, I'm going to welcome in our Geology Gents, Gavin and Graham, to get us started with the event.
Thanks, Marisa. I'm gonna start sharing my screen here, and we've got a pretty fun one today. As you said, we talk about rapid changes in the Earth, sometimes towards apocalyptic ends. So today we're talking about rapid climate changes, and this is kind of our jam, right, Graham? This is our thing.
Yeah, we're very interested in climate change and how the Earth's climate system changes over time and changes in response to major events. And yeah, like Gavin said, this is an action-packed episode today. We're gonna see a lot of cool and pretty well-known events in Earth history that some of you have maybe even heard about yourselves. So yeah, let's dive right in.
Yeah, let's do it, Graham. And also for the folks out there who might have watched last month's episode, we talked about the ice ages. So this is piggybacking on the ice ages, where we talked about the climate changes over the last 2 million years. Today we're talking about rapid climate changes throughout Earth's history, past 500 million years per se. So Graham, when we're looking at timelines of how Earth's temperature has changed over the past 500 million years, how well do we know? We know those specific events, but if we don't, it's a little bit less precise, right?
Absolutely. Yeah. So last month, I should say, we were talking about the last couple million years and looking at these glacial interglacial cycles, right, where we get cold climates and go into warm climates on the time scale of about 100,000 years. So within 100,000 years, we'll go from cold to cold or from warm to warm again.
Those are these down here to the right, Graham?
Awesome.
This is what we showed last week.
Yes, that's right. And Gavin, why is it that we're able to reconstruct those so well? Because when we look over at the curve over on the left, or maybe it's your right, I sometimes get confused on the screen, but we don't see nearly as many of those wiggles, right? We see this stretched out over 5,500 million years, and it looks a lot smoother in comparison. So it is kind of a funny thing. We can tell what's happened recently really well, and then we kind of have a rough sense of what happens deeper in time. And why is that?
Well, Graham, it's the same reason why we know what's going on today better than why we know what's going on 100 million years ago, because we have rocks today. The rock record is complete for today, but as you go back in time, things like erosion and subduction, all the tectonic things we talk about, those actually recycle rocks back into the interior of the Earth, or they make igneous and metamorphic rocks into sedimentary rocks. So you change the rock record, you recycle the rock record, and we don't have as good a coverage throughout the past 500 million years as we do throughout the past 2 million years, like we see down here. So it's not that these little spikes and these rapid changes don't happen in the past, it's just that we don't know them as well. So Graham, as you can see, there are times in the Earth's history where you have huge changes in temperature. In the last 2 million years down here on the right, you keep the same average. You swing back and forth to warm and cold, but on average, you're about the same temperature. But is that the case for the past 60 million years or the past 500 million years?
No, Gavin, that's such a good point, right? We do see, climate's varying, it goes up and down, but what we're really going to be looking closely at today is not when it, stays on its usual wiggles. We're going to look at when it goes rocketing off to really hot climates or getting really cold to really, really cold climates very suddenly and breaking away from these, typical cycles.
That's right, Graham. Okay, let's jump into it then. So, what are the causes? What's happening in the Earth system? And these aren't necessarily rapid changes, but these are sort of Earth system changes that change climate over a long period of time. And so, one thing that we talked about last week is Earth's orbital cycles. Those are what are causing those rapid climate changes that we see in the past 2 million years over the last ice age. And that's just a function of how Earth's orbit is changing, right? It's not a perfectly spinning top. It wobbles, and as it wobbles, that changes the amount of energy we get from the sun. So these are pretty predictable and not so much rapid events, right, Graham?
Yeah, that's exactly right. And these are sort of the wobbles of Earth as it spins on its axis. That's the heartbeat of our glacial interglacial cycles. That's really, the big thing that's sort of keeping us along that one wiggly line that we've been staying on, not with a constant climate, but with a climate that's sitting around a really consistent average over the last couple million years. And another really important part of the Earth system that helps to keep us going up and down on those wobbles, and helps to sort of swing us between those states, is the ocean and how the ocean moves heat around. So, as anyone here knows, when you boil a pot of water, that water stays hot for a while. When you freeze water, it takes a while for that ice to melt. And it's that ability of water to really hold on to heat well that makes it play such a big role in our climate. So the ocean has these currents that move hot, warm water across the surface down into the deep ocean. And it helps to sort of stabilize our climate in a lot of ways. We call this the ocean conveyor belt, the heat conveyor belt. There's all sorts of different names. You might hear thermohaline circulation, all sorts of great ways to describe how the ocean moves heat around from the tropics out to the poles and down under into the depths of the ocean. And that's really important for helping to keep our climate system stable. But sometimes if you mess with this too much, that can actually really throw our climate in wild directions too. It can make it go kind of haywire. And so these are the things, Gavin, that help keep our climate, help control our climate on the short term. But let's start stretching out to those 100 millions of years, right? That curve we were looking at on the slide before. What's really playing a big role there?
Great segue, Graham. So I like the way you set this up. Like, this ocean conveyor belt is moving heat from the oceans to the atmospheres. And so if you mess with the conveyor belt, you mess with the climate. And so one thing you might notice about this map is that the ocean kind of moves around the continents. But if you move the continents around, you will completely shift this very important climate driver. And so that's really the main thing that's happening. The audience might remember that we talked about supercontinents a couple of Rockin' pop-ups ago. So when you crunch all of these continents together, you really change that ocean circulation. And this has major feedbacks. It's not just the ocean, it's the ocean and the atmosphere and the ice sheets, which is all of the three driving forces that change our climate. So these are really long-term changes, Graham. But what about the rapid changes that we're talking about today?
Yeah, so I think one of the ones I often think about is like, okay, so we've got an Earth system and it kind of regulates itself. So, sometimes it takes something truly incredible to throw that climate system out of whack. And I think it's hard to imagine something more incredible than a giant rock hurtling out of space and hitting the surface of the Earth. And so sometimes large meteorite impacts have really important implications for climate. It's pretty famous in the extinction as a hypothesis for the extinction of the dinosaurs. And I'm not going to go into that yet because we're going to get a chance to talk about that a little bit more later on. Okay, so Gavin, sometimes things come hurtling out of space. How else can we change the climate suddenly?
Well, if it's not coming from above, Graham, it's going to come from below. And so we're talking about molten rocks. When you spew a bunch of lava on the surface of the Earth, we call those large igneous provinces, a very literal name. And so you have large amounts of igneous rocks, lava, spewing out onto the surface of the Earth. And you might have heard the gents talk about this in the past as well, because it causes lots of mass extinctions. And so, Graham, is it just changing the climate because the lava is warming the Earth? Is it the lava that hot?
No, it's actually has to do often, right? We're here we go. This is where we start bringing in some key parts of climate change. It's releasing these gases into the atmosphere, and some of those gases are really reflective, so they can cool down the atmosphere. And sometimes some of them can add, carbon dioxide to the atmosphere that warms it up. But Gavin, it's not just the gas in the lava that makes a difference. What else can it happen to?
That's right, Graham. These greenhouse gases don't just come from the magma, they come from things inside the Earth. So we think about greenhouse gas emissions as burning fossil fuels, which is how humans are changing the climate. But if you can imagine, if you heat up a giant section of the Earth, all the hydrocarbons, all of the fossil fuels that are stuck in those sediments will also be sort of baked out and released into the atmosphere. So this is basically spewing greenhouse gases like a bunch of factories. You're taking all of these rocks in the Earth, you're heating them up, and you're rising the greenhouse gases in the atmosphere. So Graham, one major sort of theme that we've set out here before we jump into the specific events we're going to talk about is that these quick events are actually not changing, they're not directly changing the climate, they are changing gases in the atmosphere, which is changing the climate, and they're changing the oceans, acidification and things like that, gases in the ocean, which are killing off organisms. So this is why human-induced greenhouse gas emissions is so important, because it's simulating these large, rapid events in Earth's history.
That's such a good point, Gavin. That's right. There's these releases of things into the atmosphere, and then it's the atmosphere that responds and actually changes our climate.
Exactly. Okay, so on that note, let's jump into the first one. This is a good segue because we're going to talk about the Permian-Triassic extinction event. For those of you who might not be familiar with this, this is the largest extinction event in Earth's history. And Graham, how did this all happen? What happened to cause this extinction event?
Gavin, yeah, like you said, this one was a doozy. And this is just what you were talking about in the slide before. So to give you a sense of scale, you've put this awesome map up here that shows the extent of the Siberian traps. When we say traps, that's just a word geologists like to use for a particular type of large igneous province. They're these huge basalt flows. So these dark rocks, very similar to the ones you might see in Hawaii, they come, erupting out of the ground. There are these huge flowing basalts. And yeah, that picture down in the corner shows just how thick these rocks are. So it's not, a foot thick. It's not 10 feet deep. These things are like hundreds of feet deep, like almost like a decent fraction of a mile deep in some places. So this is a ton of rock. And you can see this is sprawled across almost half of the area of Russia, or almost like between a third and a half of the area of Russia. So it's huge. Tons and tons of rock erupted. And just like you were saying, Gavin, it was baking as it was coming up through the crust. It was baking all of these carbon-rich sediments and basically burning a bunch of smokestacks worth of CO2 into the atmosphere. And so, okay, that sets the stage. But what happens then once all that carbon gets into the atmosphere? And we should say that I'll let you give the surprise for how much carbon gets released into the atmosphere at this
Well,
time.
Graham, we talk in terms of ppm. Right now there's 400 ppm CO2 in the atmosphere, and that's been on the rise. That's a pretty alarming rate. Well, during this event you have 2000 ppm CO2 just burped right into the atmosphere. And what does that do to temperature, Graham?
Yeah, so as we know, CO2 is a greenhouse gas. Temperature goes up, up, up. So you've got this great graph over here where folks tracked temperature through time. There's this big gray bar that shows where the extinction event was, and the last temperature in the Permian is a red dot, and the first temperature in the Triassic is a red dot. And it bounces up by over 10 degrees Celsius. So that's about 20 degrees Fahrenheit. That's like, the that would be changing our temperature today, what we're probably like in the high 60s or 70, bopping that up to about 90 degrees in the middle of winter here.
Man, Graham, that's pretty hot. But it's not, it's feedbacks between that temperature and the oceans that actually cause most of the mass extinctions, right? That's what we're talking about, or what we're showing in this graph, where, so these are the continents, this is supposed to be the Paleocean, and as you can see, you have the North Pole up here, the South Pole down here, and most of the extinction is at the poles, where you have a lot of oxygen loss, you have a lot of warming at the poles, and then towards the tropics, you still have a lot of extinction. About 50% of all the marine animals are dying, but it's less because you have less of that oxygen loss and less of that warming in the tropics. But Graham, so how much of the animals on Earth died during this event?
This was a tough one. Of all of the vertebrates, all the things with backbones that live on land, so all the reptiles, it was mostly reptiles, some amphibians, not, things that would look very unfamiliar to now, but 70% of them were wiped out. 70% of those species were wiped out. But Gavin, that was not even close to as bad as what happened in the oceans.
Yeah, Graham, 81% of all of the animals in the ocean died. So really, it was the oceans that were hit by acidification, warming, and oxygen loss. But again, we call this an event, but it's really important to know that this occurred over 60,000 years. So the mass extinction occurred over a long period of time, and that's just a testament to the fact that it's not like a bad day. It's like a bad 60,000 years where you get this gradual climate warming that kills off the animals.
Yeah, that's absolutely right. So yeah, these are not just bad times, but sort of these long bad times that stretch out over this event.
So let's talk about the famous Cretaceous-Paleogene mass extinction. And I know a lot of people in the audience might say, guys, you always talk about the KPG. Of course, the dinosaurs died, but I think this is a really important one to bring up because it's actually a lot different than the Permian-Triassic mass extinction, right, Graham?
Yeah, that's absolutely right. So, yep, folks are probably familiar with the end Cretaceous, right? That's when all the dinosaurs went extinct. And as you've shown here, Gavin, a lot of folks think that it was maybe a meteorite impact, the Chicxulub crater in the Yucatan Peninsula of Mexico. That could have been it. A lot of folks have probably, heard stories about the day the dinosaurs died, where there was just one bad day where a meteorite hit the Earth. But what's really key about this is in the Permian-Triassic extinction, temperatures went up, right? They went up by about 20 degrees Fahrenheit, maybe a little bit less than that, really warm. But Gavin, as I'm looking at this graph you've got here, temperatures are not going up when you go to the end of the Cretaceous. They're going down. So what's happening?
Right, Graham. So we're not necessarily driving greenhouse gases into the atmosphere like we did during the KPG. You get leading up to the Cretaceous-Paleogene, you get a decrease in temperature, and you get a pretty sort of modest change in the temperature. It's probably getting colder on Earth, and the reason that's happening is because we are actually spewing up a ton of aerosols into the atmosphere from the impact, which is basically vaporizing a lot of rock, and from probably the Deccan Traps volcanoes, which can't make it easy to live on Earth either. But both of these two double whammies are causing climate to get a little bit colder, and that's because you are changing the atmosphere. But this is happening over a much more rapid period than the Permo-Triassic, right, Graham? So we said the Permo-Triassic was a 60,000 year event. This is half that about. So, right? Go ahead.
Oh, yeah. No, and I just was going to emphasize what you said, right? Like, despite what most of the cartoons I've seen would tell me, there was not one day when a bunch of volcanoes erupted and all the dinosaurs got swept away in a river of lava. None of them were hit by meteorites falling out of the sky. Really what happened is you have these volcanoes erupting in what's now modern day India. They're, dumping a lot of junk into the atmosphere. And then things go from bad to worse when this meteorite impact comes, and that kicks up a whole lot more dust. And it really sends the Earth into this sort of winter. The sun's blotted out. It is probably very smoky. It's very dim. And things really kind of fall apart from the bottom up as the things that depend on sunlight die. And the herbivores die from that. And then the carnivores don't have any more herbivores to feed on. And so really the things that did well following this were those omnivores, things that could eat plants and meat. They were able to eke by a little bit better through these times than the really big dinosaurs and the plants. So yeah, much different sort of event than the Permo-Triassic.
Well, Graham, we knocked out the really fun ones early, but some of these climate events don't have such an obvious sort of driver, right? What about the Paleocene-Eocene thermal maximum? What's happening when you go from the Paleocene, which is about 60 from 60 to 55? What's happening during this time where we outline in this box?
Yeah, a lot of folks would be very excited if anyone could tell them exactly what was going on. But the one thing we do know is we have this sudden spike in temperature. It doesn't last very long, but as you've shown here, we've got these sort of overall trends going on, but then out of nowhere, right at this geologic, boundary in geologic time, we see this spike where it gets really warm all of a sudden. And then it cools off again not too long afterwards. But you better believe they were toasty times right around that period of time. But while folks do know that it was warm, we don't really know what caused that warming. And as folks often do, they've speculated a lot about different types of volcanoes. But there was one thing, whether or not volcanoes were involved or which volcanoes were involved, there's one key step that really makes a big difference. And what's that, Gavin?
Well, Graham, whatever happened, we are pretty certain that methane clathrates were involved in this temperature change. And so, again, going along with our theme for the day, when you pump a lot of greenhouse gases into the atmosphere, the Earth's going to get warm fast. And
so what are these methane clathrates, Gavin?
Good question, Graham, and thank you for jargon policing me, because the classic geologist just throwing out methane clathrates without describing what they are. These are basically ice that, or basically carbon that is locked up in what is not really a rock. It's basically like a solid gas, right? That's a oxymoron.
But they're kind of like stinky ice cubes. They're kind of like ice cubes made of methane. And so methane is it's made out of carbon, and it's actually a really powerful greenhouse gas. And when it breaks down in the atmosphere, it makes a slightly less potent greenhouse gas, CO2, which we know very well. So no matter how you spin it, once these little stinky ice cubes deep in the ocean start to melt, they dump a bunch of carbon into the atmosphere and they heat things up. And all that we really know is that something sort of flipped the scales and started melting these things. And once these started melting, it flew out of control and we got this huge spike in temperature.
That's right. And just to explain why we have these two images, this is a kimberlite. This is a sort of deep volcano that is rapid, and it's driven by some very deep magma bodies. And then we also have some large igneous events that are happening in Greenland and up north in the North Atlantic. So it's possible that one of these two drivers caused the clathrates to disintegrate and pumped a bunch of methane into the atmosphere, but we're really still unsure about what drove those changes. And so this is a paradox and a conundrum for some modern paleoceanographers and paleoclimatologists. And so, Graham, for our last event, let's talk about something that's a little bit closer to modern day, shall we?
Yeah. How close, Gavin?
Well, pretty close when we talk about geologic time. Maybe not to the folks who think about time on human time scales, but just 11,500 years ago, 11.2 to be exact, we have this period called the Younger Dryas, which we're sort of chugging along, and then all of a sudden the bottom falls out. We get really, really cold really fast. And so what happened, Graham?
Yeah, so Gavin, this really is, compared to these last several million years, it's a blink of an eye ago. But that's right. We know that around 20,000 years ago, all the large Laurentide ice sheet over North America started to shrink. We started coming out of a glacial, going into a warm interglacial like we are in today. But yeah, all of a sudden, it got really cold when it was supposed to be getting warmer. And what folks think happened is that this massive glacial lake next to the Laurentide ice sheet that has been named the Glacial Lake Agassiz actually sort of breached a dam, some natural dam, and flooded out into the Arctic Ocean. Now, if you look at this image of the ocean circulation, this really important ocean heat pump has a really important turn where it dives and takes warm water down into the deep ocean to move it around the rest of the world. But when you dump a bunch of cold fresh water up there, it comes grinding to a halt. And so once we break down that thermal sort of that ocean conveyor belt of heat, Gavin, what happened to our climate system?
Well, Graham, it gets a lot colder. So remember at the beginning of this conversation, we talked about the fact that when in the North Atlantic, you get these waters that come into the North Atlantic. They're really warm and they're pretty buoyant. And in the North Atlantic, they kind of settle out and turn. And during their time in the North Atlantic, they heat everything up. But when you stop them from coming into the North Atlantic altogether by pumping a bunch of fresh water into the North Atlantic, you make it colder. And that's what we're seeing here. So it's important to note that this Younger Dryas record is what's happening in Greenland. And so the Younger Dryas is mainly happening in this North Atlantic area. And as you said, Graham, in a time where you're supposed to be getting warmer, you just get a quick blip of cold. And so you must have had a rapid event. And I really like the idea of the glacial Lake Agassiz being drained into the North Atlantic in one of these catastrophic floods that we see in modern day Iceland sometimes. They're termed yokelopes. Do I have that right, Graham?
Oh, goodness. My Icelandic is not very good, but that's kind of what I think it sounds like.
Right. And so finally, we found a rapid climate change that had nothing to do with gases. This is an interesting one because it has to do with ocean circulation. But you never know. Gases might have been involved. It's still sort of an open question, this one as well. We don't have a scientific consensus for what caused the Younger Dryas, but it seems as though you had this glacial outwash. So I think we've done it. Those are some of the highlights, right, Graham?
Oh, yeah, these were great. And as promised, action-packed. These are some of what I think are the most exciting events in Earth's history.
I think so, too. And so what's coming up for the gents, Graham? We've got a blog that is coming up at the end of this month in our monthly rock record blog. And we're talking about what, Graham?
We're going to be talking about faults. And we couldn't be living in a better place to think about faults and to see faults in action. So we're going to look at faults up close. We're going to zoom out and look at them on the continent scale. And we're even going to look at them, what they look like for our landscapes around us. So I think it's going to be a lot of fun, Gavin. I'm
looking forward to it, Graham. This was a good one. Nice distraction today.
Yeah, absolutely.
Thanks, guys. I do have a question because I gather that the two of you are, in fact, paleoclimatologists, are you not?
Well, kind of. We're geochronologists, so we try to find time and we use time as a variable to answer questions. And one of the questions we're answering currently is about climate change in Antarctica, and that actually has implications on a global scale. So in a way, yes, our projects are paleoclimatology for sure.
Yeah, so I'm curious, going through the events that we've talked about today, it seems to me like some of them, the way that we derive what we know about what occurred might be by looking at what fossils are present, or might be at looking at ice core samples, or might be, there are different ways of finding that data. So I just was wondering if the two of you could speak a little bit about the methods that you use in your work that relates to these topics.
Absolutely. Absolutely. So real quick, I'll let Graham answer the methods that we use, but let's talk really quickly about the really conventional methods, because most of them that we talked about, especially in the last 2 million years, are drill cores into the sediments in the ocean. So we make measurements on those drill cores, or ice cores, which we talked about last week in the large ice sheets on Antarctica and in Greenland. There's also, when you go back way in time, we have things like calcite or carbonates that are in these really old sediments. So then you're starting to piece things together, but it's most of the time in the sedimentary record. But Graham, what about our stuff? Because we do stuff that's pretty unconventional, right?
Yeah, so a lot of the stuff we work with they're actually rocks, but they're rocks that form sort of at the beds of glaciers, and so so what we're doing is we're trying to understand how old they are, but then there's other things we can look at with them to get a glimpse of what they're forming from, and it's using the same sorts of tracers that folks use to keep track of where water is going in the Earth system, whether it's going into ice sheets and things like that. So we use a lot of these sort of chemical tracers to keep track of how these things are forming, and that tells us a little bit about the ice mass over them, what those glaciers are doing. And so, and then another part of it is just thinking about, where are ice sheets when? It's always helpful to have a good map of how big ice sheets are, because if we know what their sort of how large they are, we know, how much ice they're holding, what sort of state our climate system is in.
Cool. Yeah, and it sounds like all of these different methods are often pieced together to then have these descriptions that you guys have been sharing with us today. It's not that they're all based off of one set of data of ice cores. It's probably that there's little clues and hints all over the place that come together.
Yeah, that's absolutely right. The Earth has been very generous with the rock record it's left us, but we don't get to see everything. So we can only go as far back in time as the ice sheets hold ice, and we can only go as far as the oceans hold sediments, and then we need to start rooting around for rocks that are older and older and harder to find. But we do our best to piece together the jigsaw of Earth history.
Okay. Well, thanks for these tales today, gents. And I look forward to reading this month's blog. And we've got a couple now in the archives that everyone watching can go to the website and find. And we will see you next month in February for our next Rockin' Pop-Up. So thanks.
Awesome. See you then.